Talk about particle picking and about 3 versions of our apple picker. But first, for people who don't know what particle picking is, I'll just give a short explanation. When we want to get high resolution reconstruction, we usually need tens of thousands or hundreds of thousands of particle projections. But unfortunately, we're not given a stack of particle projection, we're given these noisy micrographs that contain multiple particle projections in unknown locations. So the step of particle picking is just to identify where the particle locations actually are and try to return all the centers of each particle. The problem is that most micrographs you can't really see anything, so good luck trying to pick that. Some existing approaches are, first we start with, there was manual picking. I guess that was the first attempt. So it's just a person sitting in front of thousands of micrographs and choosing one particle at a time, which is pretty tedious, and it depends on the picker. If he picks the wrong stuff, you're going to get very bad reconstructions. And this is actually still being used today, and just last year, a paper came out on crowdsourcing for particle picking. So that's actually manual picking, just not done by us, done by people that we pay. The neural networks, Bridget discussed before, so there's a lot of neural networks that try to do particle picking. Training time is usually a few hours. It could be about 10 hours, and once again, since a person is picking the particles, it could be a problem here. And the results not only depend on the person, they also depend on whatever feature the deep network learns, and we don't actually know what that feature is. So it's not that obvious what if we can do kind of cross-training on different data sets. Our apple picker is closest to the template picking approach, and there are several variations on that, so if anybody's interested, there's a survey paper by Nicholson. But the basic template matching just means that if you have a very clean template of the particle, you can cross-correlate the template with a micrograph. And the nice thing is the maximums of the cross-correlation will appear wherever the template in the particle fits best the pattern of the micrograph. So if you look at the bottom picture, that's just the cross-correlation. Wherever you see the the yellow dots, that's actually a particle. And if you just choose the maximums of the cross-correlation function, you can get a very nice particle picking, sometimes. But first of all, you need to have a template. And if you knew what your particle looked like, you wouldn't have to do anything to begin with. And second of all, there's a lot of false detection because of the noise. So if you had a template, this would be a good way. There are several ways to produce templates, but each way has its own problem. So what we wanted to do with the apple picker is to use information from the cross-correlation function, but also not to use any templates at all. So we checked what happens if we took a window from the particle, this blue window that's very noisy projection, and we cross-correlated it once again with a micrograph. So we found that we can still find some particles. Okay, the cross-correlation function is not going to be as clean, it's not going to be as localized as if we had a clean projection, but it is going to have several distinct peaks wherever we have a very similar particle projection. So I'll get back to that. That's a very important part of our particle picking, but first let's discuss the noise a little bit. So what we found is actually each 2 data sets can have different particle projections. They can have different artifacts, but they're all going to have the same noise model. So the noise model is, the shot noise is a Poisson process. The shot noise is actually the main limiting factor of the SNR in a micrograph. And the important thing about that is that it has no repeating pattern, or at least with high probability, it's not going to have any repeating pattern, which we figure could very much help us if we do cross-correlation. Because if we cross-correlate the micrograph with a window of noise, which is what we did here on the bottom, we don't actually see any peaks. Okay, because the noise isn't going to fit any pattern better. It's not going to fit noise better. It's not going to fit the particle better. So what the apple picker does is it takes some window in the micrograph that we don't know what the window contains, and We call it a query window because we're actually just trying to find out what that window has. And we cross-correlate our query window with the entire micrograph, and then we look at the result of the cross-correlation. And what we want to see is if the result of the cross-correlation has a lot of peaks, or if it's just a pretty constant signal. And if it's a constant signal, we're going to say that what we actually found was just noise. And if it has a lot of peaks, we're going to know that we found a particle in the query window to begin with. Okay, so very different from template matching, because in template matching, we take a template, cross-correlate with the micrograph in order to find particles from the micrograph. And what we do is we take a window from the micrograph and cross-correlate with the micrograph to identify just what's in that window. And here are some results. So I don't know if you can see it, but there's, this is a small portion of the micrograph, and here, for instance, is a particle, and here also. And here's the cross-correlation. It's much higher wherever there's a particle, and much lower wherever there's noise. So that was the first version of our apple picker, and it worked very nicely. The problem is it took forever. Because what happens is you're cross-correlating a window with a micrograph. Cross-correlation is O of n squared log n operations, where n by n is the size of your micrograph, which for us is like 4K. Or if you do binning, it's like 2K. But then we're also doing it for every single window in the micrograph. So now we have more than 10 to the power of 13 operations per micrograph. Which is why earlier I showed you a tiny part of a micrograph, just because I didn't have the patience to let it run longer. So the apple picker 1.0, the one that we have published, we fixed this problem, and now it just takes about 7 seconds per micrograph. And we did two things to fix the problem. First of all, we don't cross-correlate with the micrograph. Okay, so like I said, in template matching, we had to cross-correlate with a whole micrograph because we wanted to find particles from that micrograph. But we're just trying to find out what our query window contains. So we cross-correlate with some representative areas in the micrograph. We identify these areas automatically, and our goal is just to find a few windows, each window the size of the particle. Some have noise, some have particles, some can have contaminants. We don't care what each window have, we just care what the distribution of windows is. So to find it, what we do is we take the whole micrograph and we look at very large areas distinctly, okay? So we call each of these areas a container. And in each of these areas, we look at the mean and the variance of all possible windows. And what we find is, since we already knew, that the particle has lower intensity and higher variance than the noise, if we take two windows with highest and lowest variance and two windows with highest and lowest means, we'll, with large probability, take two windows of noise and two windows of either a particle or an artifact. And since we're looking in different locations over the micrograph and assuming that the micrograph isn't just one big artifact, we're going to find particles for sure, we're going to find noise for sure, and we don't care if we find artifacts as well. So now what we're going to do is we're just going to take like L windows, usually that's about 200 or 300 windows, each of them a few tens by a few tens of pixels, and cross-correlate with our query window. Okay, so now the complexity of the cross-correlation, which had been n squared log n, is L times m squared log m, okay, but it's much lower because m is now a few tens instead of a few thousands. And once again, since we do it for every possible window in the micrograph, we need to do it n squared times this whole operation. So this is just the graph of what we actually do. We extract this whole set of windows, and we take some window in the micrograph, which we don't know what it is, and we cross-correlate with each one of these windows. And our only question was, does the cross-correlation function have a peak or doesn't have a peak? So in order to find that, we just take the maximum of the cross-correlation function, and we subtract the mean of the cross-correlation function. So if there was no peak, we'd have a pretty low value, and if there is a peak, we're going to have a nice high value. So here is histograms of this cross-correlation. Okay, so it's one value per window from the set. And when there was a particle to begin with, we have these few nice peaks, but when there was no particle, so we have pretty low values. And what we can do is just set some threshold, let's say at 8, just by looking at the data, and characterize each window by how many of these cross correlations pass the threshold. So if one window had high cross correlation with a lot of the reference windows, it's what we call the Fs, it's definitely going to be a particle window, but if it had very few peaks, it's definitely going to be a noise window. And that's how we can decide what's particle and what's noise. And then we went onward to improve, and we said all this works very well, but we don't actually have to do this cross-correlation theme with each window in the micrograph. We can just do it with half-overlapping windows of the micrograph, right? Because then we'll still find each one of the particles, right? Because even if one window is kind of here and only gets this small part, the next window is going to capture the particle very nicely. So this is actually what we do. We do this cross-correlation scheme just for a subset of the windows. And then we decide which windows do have a particle and which windows do have noise. And we can use that to train any classifier we want. So we can train a deep network, but we found that an SVM classifier works very well and is a lot faster to train. So once we do all this, our complexity for the cross-correlation is ln square log m. And since we don't use a lot of training example, the complexity for the SVM classifier is a lot smaller than this. So this is kind of results for the apple picker. This is the representative micrograph that we took from the Empire beta-gal dataset. And we use the apple picker, and here's the results of the classification. Okay, so all of the marked areas are all the pixels that we found are particles. And then we took these areas, and areas that were much too big compared to the particle size we just threw out. And we were able to pick all of these particles. And then we found a problem with the apple picker, which is, it works very nicely, and we got very nice reconstructions, but just if you look right here, these two particles were found as one region. So the center that we give is right in the middle of the two particles. So we found this also happens in other particle pickers, but it kind of gives you two parts of the particle, and the center of the picked particle is noise. So that's where we moved on to the apple picker 2.0, and we fixed that problem. Okay, but first some results. So the top is a reconstruction of the beta-gal particle that we made in Relion, but from the particles that the apple picker chose. And the data set gives also a manual picking of about 40,000 particles, and we also did a reconstruction of those. And that's what we have on the bottom. So the reconstructions look mostly alike. So show the FSC curve. Our particle, so the apple picker, they kind of start looking a lot alike, but the apple picker here gets to 4.1 angstrom resolution, and the manual resolution will give 4.2 angstrom resolution. So like I said, this code is available, and there's a GPU version. It takes about 7 seconds to run per micrograph. And then we continued on to the Apple 2.0. And we figured that, like I said, the problem is that we find that these particles sometimes that are very badly aligned. And particle pickers themselves usually don't have any alignment step. The reason they don't have an alignment step is just that we so don't want to miss rare views. We would rather have false detections than miss the rare views, because they're very important to the reconstruction resolution. And if you add restrictions that have to do with alignment, you're going to end up throwing out particles that might be good particles. So till now, alignment was not a part of particle picking, and in the Apple Picker 2.0, we added a new alignment procedure that does allow us to It allows us to take these are class averages done by Relion from our particle pickings, by the way, and these are the bad classes that I mentioned earlier. Okay, so obviously we're not going to pick them and we're going to throw them out, even though they include perfectly good particles. Furthermore, some of our class averages are kind of not fully contained in the mask. So here. Okay, so we added in Apple 2.0 a new alignment procedure, and if you notice, we got rid of all of the issues that we had earlier, the ones with the two partially contained particles, and we were also able to get a much better centering for each one of the particles. So what we actually did is we obviously didn't create at this point any 3D model of the particle, but what we said is that the center of mass of the 3D particle is always projected to the center of mass of a projection image. So all we need to find is the center of mass of the projection image, which sounds very easy, but it's pretty impossible due to the noise and due to the CTF. So what we created is this new procedure that estimates the location of the center of mass, and it does a pretty good job, good enough that we were able to take all of these particles and move the alignment so that we throw out one of the particles because we can't get both of them, but we do keep one of them at least. So this is our reconstruction on the top. So here you can see very slight differences. I should have made it bigger. But mostly in the center, it's a little better separated up here than it is in these images. Okay, and this is our FSC curve. So now that we do the alignment, we were able to keep many more particles. And we got 3.5 angstrom resolution reconstruction as compared to the 4.1 angstrom resolution reconstruction from the Apple 1.0 and the 4.2 reconstruction from the manual picking. And then another experiment that we did is what would happen if we found all of these all of these unaligned particles and we just threw them out. Because we do know that Relion we will probably throw out the class averages that contain them. So if we throw them out to begin with, we'll have less outliers, we'll have less work for Relion to do, and maybe we could speed up the reconstruction without actually hurting the resolution. So we tried doing this, and we were able to get the class average done in 70% of the time, and still our reconstruction was the exact same resolution, 4.1 angstrom, because we did in fact throw out all the particles that we would have thrown out. We threw out in the Apple 2.0 all the particles that we would have thrown out in the class averaging from Relion. So that's why this gives kind of a two options. If you want to just get very quick class averages in order to check if your micrographs are good to begin with, you can just throw out all the outliers and get a fast 2D templates. And on the other hand, if you want to get a better reconstruction, you can use our alignment method and you can improve resolution by keeping more particles. Okay. So yeah, finished a little quickly, but yeah, so we have the Apple Picker 1.0 that's available in Python and in MATLAB. So the Python version is available as part of the Aspire toolbox. Like I said, the runtime is approximately 7 seconds, but that's when you do it on one GPU and one CPU. We also have code that allows you to run several micrographs at one time on the same GPU, and code that allows you to run on several CPUs and on several GPUs, and all that gives a very nice speed up. So we were actually able to get 84 micrographs done in about 80 seconds using as many resources as we were able to get at the time. Yeah, so if anybody wants to use it and has questions about it, like I said, we have it in GitHub, so you can open an issue there, or you can just email me, and we're going to have the Apple Picker 2.0 coming soon, and also the actual alignment work. So that's work that I'm doing also with Amit and Nir, and that's included in the Apple 2.0, but it's also going to be available as a standalone. So that's all I have.